Good morning, good afternoon, good evening to everyone around the world that is joining us today. In this webinar here today, we're going to showcase how you can automatically correct misalignments that already exist in the ortho imagery that you're using within your stacks in order to improve things like time series analysis. And we're going to be showcasing a new workflow that we've recently released, which is called our SuperRegistration. In order to engage with our team, all of your lines will be muted during the presentation. If you wish to ask a question at all throughout the webinar, please do so by expanding the questions panel, which opens up the questions window where you can type your question to the panelists here today. We will do our best throughout the webinar to either answer your question directly in the questions panel or during the live Q&A session at the end of this webinar. If we don't get to your question by the end or throughout this webinar, we'll be sure to answer all questions that are asked and post it on our website along with the recording of this webinar. Today's presenters, we have a smaller crew with us today. So we have Jason Flatt, who's one of our solution engineers. He's no stranger to these webinars, and he'll be basically the star of the show, running the demonstration for us later in this webinar. Welcome, Jason.
Welcome. Hello, everyone. Good to see everyone here today, and looking forward to going through the demonstration later on in this presentation.
Wonderful. Thank you, Jason. And myself, I'm the host of the webinar, so I'm a product marketing manager at Catalyst. My name is Sean Malamed, and once again, on behalf of our team, we really are happy that you're here with us today. We hope that you learned something valuable from it. In terms of our agenda for this webinar, we're going to start off with a very brief introduction to Catalyst. So very quickly go through about this new brand that we've recently launched. We're then going to dive right into the topic at hand. So we're going to start by defining and understanding the problem with misalignments of ortho imagery. Then we're going to start to ask ourselves the question of why. Why do we care about this? Why should we try to change these shifts? Why is that important? So we're going to be demonstrating some examples around that. Then I'm going to hand things over to the star, Jason, who is going to be showcasing a demonstration and discussing some validation results that we've produced. And then finally, we're going to end off by showcasing some of the different solution mix or the different solutions that you can access the SuperRegistration and other workflows that it's embedded within. And then finally, we're going to open things up to a questions and answers section where, once again, if you have any questions throughout the webinar, please feel free to enter it into the questions panel, or you can enter your questions at that time. So Catalyst is a brand that was introduced by PCI Geomatics back in October of 2020. And the whole purpose about it is to bring actionable information based on Earth observation to more users, to bring it to a wider audience base, more end users, bring it downstream. And the whole purpose is to make sure that we can have more information to make better decisions in order to ensure a sustainable and manageable planet. With this, we've done some rebranding of some of our products and added some new products into our product mix. So we have our Catalyst Professional, which was formerly Geomatica. This is our geospatial desktop solution that is specializing in remote sensing and Earth observation sciences. We have Catalyst Enterprise, which is our production system capable of distributed production or processing, which is really designed for automating workflows and scaling those workflows as to meet your production demand. Then we have Catalyst Insights, which is our web-based services, or our web services for accessing actionable information, or the information itself that is derived by our tools. So this is where we can subscribe to information products. And then Catalyst Microservices, which is our new solution recently launched for processing Earth imagery in the cloud. All right, so looking at the problem itself about misalignments in ortho imagery. So this really comes from when you compare ortho imagery from different projects, different archives, different sources. And one of the problems is that they often showcase misalignments. Now, even with some of the most trusted ortho-image sources, we still experience shifts. So in this demonstration that Jason's going to showcase today, even looking between Sentinel imagery, so Sentinel 2A and Sentinel 2B, we can still measure noticeable shifts such as up to 1.27 pixels. Comparing Sentinel 2B to Landsat 8, we see shifts of, we measured shifts of up to 1.13 pixels, looking at just a small subset. And these translate to like 12 to almost 17 meters in shifts. And keep in mind, these are some of the most rigorously controlled ortho imagery on the planet. So even between these archives and sources, we still have shifts. Now, why would we want to mix these images? And that's because right now, if you're analyzing a current event or you're analyzing a disaster or anything that's unfolding, sometimes you're just trying to access the most recent and relevant data source that you can get, and you need to include that into a stack of other sources. And this is where mixing these images becomes very important. Now let's imagine and let's extrapolate this problem and introduce now different platforms where we're mixing things like drone data with satellite imagery or with aerial imagery. So we have another example we're going to showcase, which is looking at an orthomosaic that was generated, captured from a drone data or drone imagery, and then comparing that to a WorldView 2 image of the same area. And with this, we had, because once again, completely different models, completely different control sources, there was an error that was introduced of about 16.3 pixels or 8.15 meters between the ortho products produced from these different platforms. Now, why do these misalignments happen? Well, as I've already alluded to, we have different control sources that are often being used by these different projects. Reference information is often updated over time and improved over time. The digital elevation models that are being used for the 3D orthorectification are often improved. The resolution of those images can be, or DEMs can be different. Survey ground control points, they often are enhanced and improved over time. And also there's different accuracy requirements for different types of projects. If you have, for example, updating survey imagery for updating cadastral maps, then that might have a more rigorous accuracy requirement than if you're doing say a large scale or low resolution analysis of deforestation. They might have slightly different accuracy requirements. And same thing, different softwares, different algorithms, different sensor models, all these things can introduce differences in the final alignment of the ortho pixels or the pixels in the ortho images. And then one of the problems is that you cannot rerun them through an ortho process. So if you're building a stack of imagery for analysis and you're pulling data from different sources, from ortho images from different archives and different sources, well, you can't just rerun them through an ortho process. The pixels have already been shifted. The rational polynomial coefficients are no longer valid. The sensor details are not available. And as a result, you're then required to use generic algorithms like thin plate spline and polynomial models. And from my experience with these, they can often introduce more error than the original orthos themselves, or they can perhaps improve certain more localized areas, but then introduce more error in other areas, depending on your control points. Now let's turn gears to why even fix the shift. A couple pixels, is that really a big deal to fix? Well, yes. It's because these are errors that are introduced in an early stage in the workflow, and that these problems, as a result, they propagate and become even more problematic in the final and ultimate delivery in the output in terms of what you're producing. And we're seeing these in things such as time series analysis, machine learning and AI, cadastral mapping and surveying. So let's just take a look at machine learning and AI. That if you have, there's a common saying known as garbage in, garbage out. And if you have slight shifts or large shifts, whatever, shifts in your stack, and you're training this data to look for changes, to look for movement, to look for growth, to look for a variety of different things, it can misidentify this because the data that's being provided as an input is not of the quality requirements. time series analysis can create misidentified change, which is something actually Jason's going to showcase later on. And as a result, we end up having these situations where we get incorrect feature boundaries in terms of looking at movements or positions. We get false change detection along the fringes or edges of features. And this can become problematic in highly automated workflows. Now let's take a look at a very specific example of that. So imagine right now, I'm sure many of you are aware of the Ever Given ship that got stuck in the Suez Canal back in March. Well, this ship, as a result, caused a blockade, which caused billions in dollars of losses and write-offs and delays. The ship alone had over $1 billion worth of inventory on it. So imagine going downstream and looking at end users and how they would care about this and how this might impact them. Well, ships can introduce errors in the AI algorithms that they're using to try to get a head start of the competition. So imagine you're speculating on stocks that, trying to identify when they're going to hit their lowest point, because perhaps you're looking at asset management companies that are seeing shortages, and as a result, their stock is dropping in that regard. Or perhaps you're looking at you're from a risk management side and you're on the supply chain side of things, and you're trying to understand what kind of shortages you can anticipate and how is this going to impact your top line. So one of the advantages of satellite imagery is that you could use that to try to understand what progress they're making on dislodging the Ever Given ship. So if you start to identify if there's a misalignment that's created in the images that you're looking at in order to perform this change detection, you might have, and if you're using automated algorithms, it might identify or false progress of dislodging the ship. So it might see that there's movement of the ship that isn't actually there. Now, speaking of automation, another important component, now this is something we're starting to see, is these pipelines, these automated pipelines that are being created to produce things like continuous change detection and classification, or automatically updating information. And as we're capturing vast amounts of data and vast amounts of imagery from a variety of different sensors, and that's just going to increase, we need these automated pipelines in order to make sure that we can continue to capture this information or this data and turn it into something useful, turn it into valuable insights. So by not being able to correctly fix things like the geometric accuracy of these images, or make sure that they're at least all aligned with one another, once again, we're going to introduce errors and we're going to introduce problems that are going to propagate into the final deliverables or into the final analysis, which can result in poor decisions being made. Now, this is also a part that we're going to come back to at the end of the webinar, which is that the SuperRegistration algorithm and the importance of it is included in the analysis-ready data workflow. So by converting imagery into something that's an information commodity that can then be used for extracting information immediately from it, the SuperRegistration is an important component of that, once again, to ensure that we have data that's immediately available for analysis. And the analysis-ready data workflow really just expands on it. So SuperRegistration is a component of that. So we have customers that are using it as a standalone to just improve their accuracy of their images within their ortho-images within their stocks or within their archives, but then also as a piece of a larger workflow within analysis-ready data. So anyways, with that, I'm going to hand things over to Jason, who is going to showcase, before we do that, before we go into the demonstration, I got a little ahead of myself. We're going to open things up to the floor and do a quick survey question and just see if anyone has, ask a very simple question, which is, do you currently experience problems with your ortho-image alignment that negatively impact your work? So this is really just a simple yes/no question. So if you are experiencing issues where your ortho imagery is not aligning well with other ortho imagery, and is that negatively impacting your final results? Is this a problem that's important to you to have resolved? So we'd love to get your results. So they're piling in now. We got about half of you have now voted, so that's great. Great engagement. Appreciate that. And it's this is what we were hoping for. It's a pretty significant number are saying yes. There's a small minority of people that are saying no. But we have right now about 60% of you have voted, and right now it's at 79% yes, 21% no. So we're going to keep the polls open for just another 5 seconds, and then we're going to close them. So if you haven't got your vote in, please get it in now, and then we'll close the polls and share the results with everyone here. All right, with that, we're going to close the polls, and let's share so everyone can see. So in the end, we had about 60%, just over 60% of the people voted, and we have about 77% said yes, with 23% saying no, which is great because that's what the whole purpose of this webinar is about. All right, so now with that, I can hand things over to Jason in order to showcase the actual demonstration. Take it away, Jason.
Thanks, Sean. Hello, everyone. So for today, this demonstration, I'm going to showcase 2 examples that cover misalignment. So the first example is based on the shift and misalignment from ortho-imagery of SAME and of Landsat and Sentinel 2A and 2B imagery. And as Sean's already mentioned, it will be covering the Ever Given. This is the example of the Suez Canal during that period of time when it was stuck. And so we're going to see how the imagery is viewed in different sensors. And we're going to see some misalignment. And then we're going to go and look at another example with UAV and Worldview 2 imagery. And lastly, just discuss and showcase the importance of correcting this misalignment in our ortho images. So I'm just going to exit out of the PowerPoint and open up my first gallery. Here in this first area, we see that the ship is stuck. The Ever Given is stuck. We're a ship surrounding it, trying to get it out. And I've used both Sentinel 2 and Landsat 8 pan sharpen imagery. And of course, these images have already been ortho-rectified, so we cannot fix the shift using traditional alignment methods. So we're going to use leverage the SuperRegistration tools. So I'm going to go to our first little area. Here, I create a little AOI of where the ship is, and I have images, a reference image of before the event, and we're just going to cycle through the Sentinel 2 and Landsat scenes. So I'm going to turn each one on so we can see the ship stuck. Again, continuing to be stuck. Finally, it's moved on the 29th, and then the 30th, or sorry, the 3rd, it's all clear. And as I cycle through those images, we can see a shift. As although the ship is being continually pushed and moved, we can look at a more stable location to then make a decision if there is actual misalignment between the images. And so we're going to look at a stable location at the intersection on the left. So here we are with the same images again, and we're just going to cycle through. And if you notice, my cursor is right in the center of that intersection. So let's even zoom in a little bit more. All right, so starting from the Sentinel reference, we're going to turn on the next. Continually turning on the images. All right, so what we see then visually is that there is a shift, and this is a perfect example of understanding the problem, as this shift will introduce that error at an early stage, which will have that impact on our future analysis, and why we must correct it before we can do any other processing steps. So now I process the imagery using our SuperRegistration workflow, and now let's look at the results over that exact same area, okay? So I'm going to select the next area. Here, we're going to zoom in again. I have my cursor right in the intersection, and again, I'm going to cycle through. We have 1, 2, 3, 4, 5. So immediately what we see visually is that shift previously is no longer present through visual inspection. However, it's always necessary to perform a statistical measurement as well. So what I've done is performed a it generated an accuracy assessment for each image using the March 19th as reference. So I've calculated the circular error 90 and plotted them out in this graph right here. What we see through the assessment, the uncorrected ortho images are orange, and that's their circular error 90 in pixels, while the blue is that the same images super registered circular error 90. And immediately what we can see is, for instance, on the first image, that trend where the original ortho image has a circular error of 1.27 pixels. However, once we correct it, we are able to greatly reduce that error to be below the sub-pixel, so around 1.1667 pixel error. And we see that trend across the entire table. So now what I want to do with this information, we can then look at another example. In this example, I'm aligning worldview 2 pan sharpened imagery with a high resolution UAV image we have below. I'm going to first open up and load the already orthoed pan sharpened product, and immediately if we zoom into the corner here with the road, there we visually identify a significant shift. However, once we process the ortho mosaic through SuperRegistration, we're able to improve that alignment to get them aligned properly. And so, of course, we need to perform, statistical analysis and accuracy assessment to ensure that we are improving the image themselves. So I again plotted out the circular error 90 with our accuracy assessment, and we can immediately see on the left the super registered worldview 2 image, and on the right is the ortho, and we can see from 16 pixels or 16.3 pixel or circular error in pixels to below 1, below a sub-pixel of 0.77 error. So to bring back though, why this registration again matters is I've also performed a change detection between the super registered worldview 2 and the UAV image. And so let's load up the super registered results. And I want us to just bring our attention to the top area here where that road is. What we see, the change in how I'm representing it, is that green represents areas of low change. So along the road, of course, we expect to see very little change occurring, while blue and red are areas of positive and negative change. So we're seeing similar trends. But if I were to perform that change detection again, but with the misaligned or original ortho worldview 2 image, we can immediately see over that same area those false positives and negatives being identified over that road. So in summary, what we've explored today is just how a data stack can contain across the imagery can contain shifts, even if the data you acquire is from well-known sensors. And of course, that can introduce error in your analysis. And the super registration process is able to improve that alignment to sub-pixel accuracy, which provides you users the confidence for detecting change.
Wonderful. Thank you so much for that, Jason. So just as a recap, what he went through today in the demonstration was showcasing the initial shift between Landsat 8, Sentinel-2A, and Sentinel-2B imagery, and then the resulting super registration and the alignment that we're able to get, which was down to about 0.2 pixels. And then once again, did the same concept with UAV versus worldview 2 imagery, where there was a much larger initial shift, and then demonstrating bringing that down once again to sub-pixel accuracy. And then finally, just demonstrating very quick, simple example of how how those errors can propagate. Now, we used a very obvious example for this case because we just wanted to showcase it or make sure that it really jumped out at you. But even those errors in a small scale can become quite problematic when you're looking at analyzing things like what I showcased earlier, which is trying to identify small movements of items or features or growth on features, and those can propagate into automated algorithms. So A larger project, as I alluded to earlier, was analysis-ready data is a larger workflow that includes the super registration as a key component within it. So we've recently delivered a analysis-ready data workflow to SANZA, the South African National Space Agency. We're actually going to be releasing a case study soon and having a webinar with them in May, so stay tuned for that. Where basically our solution is going to be converting their entire archive of spot 1 through 7 that they've been collecting since the early 90s imagery into analysis-ready data. So here's just a subset of some of the early results that we got with them. So it's a subset of 727 spot 1 through spot 7, so not just a single sensor, but a series of sensors with different spectral characteristics, different bands, different resolutions. And we were able to get that subset to a circular error probable 90 of about 0.13 pixels, doing an entirely automated process. And then we actually extended, so the super registration and the geometric alignment is really only one very important, but one part of the equation. The other really important component is the radiometric normalization. And this is basically removing atmospheric effects, bidirectional reflectance effects, terrain illumination, solar and viewing geometries and the different illumination effects from those. So we're trying to normalize for all those things in order to make sure that when we're comparing imagery in the stack, that not only are the pixels correctly aligned, but the spectral characteristics are the same between the different images. So we're really comparing apples to apples, and that's what we're able to deliver also with our analysis-ready data workflow in terms of, and once again, super registration is a very important component of that. We also have some customers that are using it for improving their own ortho images within that are sourced from different projects or archives. And then we actually have a really fun customer who's doing the same concept that Jason showed, where they're using or they're aligning their satellite and UAV and aerial imagery into stacks for further analysis, as well as some tip and cue concepts. So what are the different ways you can access super registration? So Catalyst Professional. So super registration is accessible through our Python library, so it can be automated through the Python workflow, as well as easy. And it's really, once again, this is really more used for educational, for research, and for also developing bespoke solutions and workflows. So that's how it's most commonly used. And this can be accessed through different subscription models as well as perpetual. We also have it available as a part of our analysis-ready data workflow, but it can be used also as a standalone within our Catalyst Enterprise, which is our scalable production system that's capable of doing distributed processing, and it's really designed more for highly automated tasks that you wish to productize or put into a production environment of any sizes. And what's beautiful about it with our new subscriptions and per core licensing is it can scale up and down with your demand. So it can really match how your business works and how your organization would want to access the solution. And now we also have it available through Catalyst Microservices. So this is our cloud-based, our solution that's optimized for processing Earth imagery on the cloud, where we've containerized this technology and we've made it available on a variety of different cloud providers in order to work with the imagery that's already on the cloud. And what's great about this is that the data moves, or sorry, the processing moves to the data. So as opposed to having to move the very large and expensive data to the processing or to a processing server, the process itself, the microservice, is very portable, and it can move to the actual data itself, which can be save significant amount of time, money, and ultimately reducing waste. And that's just one of the many benefits of processing data in the cloud. It is now available on AWS, and it will be coming very soon to additional major cloud providers and industry partners. Just a small or a short list of some of the ones that we're currently working on here on this slide as well. So we're going to finish things off with a final survey question, and then we'll go into our Q&A. We just want to understand, how are you using ortho imagery today? And this is a multiple choice, select all that apply kind of question. So I'm going to just quickly launch the poll. So once again, how are you creating it? Or how are you using ortho imagery? So perhaps you're creating ortho mosaics, and it's mainly used for that. Doing time series analysis, it's used for cadastral mapping and surveying, land cover, land use mapping, or is there something else that you're doing with it? In which case, we'd love to know. So you can also provide that detail in the questions panel. Once again, we just want to understand how you're what's going on in your organization, how you're using ortho imagery today, or how you intend to use ortho imagery as well. All right, so we've accumulated a number of votes already. We seem to have majority, so 30% are creating ortho mosaics. We have 27% time series analysis, 10% cadastral mapping surveying, 16% land cover. Oh, that's starting to jump. And then a number of you are also posting others. So we'll keep the poll open for another 5 seconds. So if you haven't got your vote in, please get it in now. And we're going to close it in 3, 2, 1, and we'll share the results with you. All right, so as you can see, we have actually time series analysis was the final winner, overtook ortho mosaicing at 29%, but still a lot of you are doing ortho mosaics. And I have a feeling that many of you are choosing multiple selections, because I know that they're often, not exclusive to one type of process. 9% cadastral mapping, and then land cover, land use mapping was 21%, and then there's a few other options. So once again, we'd love to, understand what other things you're doing with ortho imagery. All right, so at this stage, we're going to open things up to questions and answers. So we'll just open up the questions panel here. So we have a few questions that are starting to come in. So this one I think is a good question for Jason. Maybe you can join me back on stage, Jason, for the Q&A session. But
of course.
Wonderful, wonderful. So this one is, how do you run the super registration? That's fair. We didn't actually show running it. We just more showcase the results. So maybe you can describe some of the different ways that customers can access super registration between the different solutions.
Of course. So one way to run super registration is with our enterprise platform. It's a very simple interface where you just provide your data that you want to register, your reference data and output, and it will automatically align. But we also have it in professional, but through our Python API. So we have our own you can generate your own custom workflows for the alignment as well.
Yeah, and you can actually access, so if you go to our website, catalyst.earth, you can access, you can download a free trial if you haven't already worked with the software for Catalyst Professional, or you can contact Jason's team for a demonstration. They would love to showcase a little bit more of the details and show you exactly step for step how to work that workflow. And it's a automated workflow, so it's using automatic collection. It's another question that came in. So the question is, there's actually a number of questions in this one. So is the shift always present? So is it basically, to answer that question, it's not always present, but it's most likely going to be present when you're comparing images from different sources. If the imagery is created from the same control source with the same amount of rigor, same accuracy requirements, then there's a higher probability of the imagery aligning without that shift. But if you're pulling imagery from different sources, different projects, there's likely to be some level of shift between the imagery. Another question was, is it always present in images from different sensors and platforms, or just most of the time? So because different sensors and platforms, they're different organizations, different companies that are performing these workflows, often not necessarily collaborating or coordinating with one another on them. So yeah, there's a high probability that some shift will be introduced because in a perfect world, we would have a universal reference source and standards for that. And it's just unfortunately not the practical case in the world today. Sorry, just reading through some of the new questions that have come in. So this one, I think, is someone who might be relatively new to the ortho-imagery game. So the question is, what are ortho-imagery, or what is ortho-imagery? That's a great question. So ortho-imagery is actually a short form. It's the long form of it is ortho-rectified imagery, and this is really just correcting or performing a geometric correction of the imagery to transform it. So it's a photogrammetric approach to transforming the imagery or morphing the imagery based on a particular model using reference information to correct it so that the pixels on the image are accurate, or the features on the image have coordinates that are accurate with those features on the ground. And we use things like rational polynomial coefficients and reference sources like control points that could be survey points or captured from reference imagery and digital elevation models in order to, I guess, warp the image in a way that it's now properly representative of those features on Earth and the coordinates that would be associated with them. So another one is, I guess this one's around the ARD workflow. So what are the other steps of analysis-ready data workflow? So perhaps, Jason, while I review a couple other questions, you can just quickly talk them about, give them an overview, high-level overview of the analysis-ready data workflow.
Of course. So the analysis-ready data workflow is, there's three main steps to it that are made up of multiple smaller steps. So the first is that geometric correction, and that's taking the imagery and aligning it with utilizing our own GCP automated GCP collection and the SuperRegistration techniques, just to ensure that that geometric alignment is correct. And then the second step is that radiometric correction, that radiometric normalization, where we can normalize satellite imagery, utilize with MODIS imagery, for instance, for that normal, so that when you perform your analysis, that the change isn't based on the atmosphere. It's actually showcased, the radiometric information is of the ground features themselves. So once you've corrected geometric, you've corrected for radiometry, the last step is just packaging it. And so what we do, what Catalyst, one of our goals is we follow with the CARD4L or the CL standards. So we package up the final results, and that's following certain metadata procedures, ensuring that the correct metadata information is packaged so that other users can then acquire that and following the CARD4L standards and analyze it.
Wonderful. So this will be the last question we'll be able to take live today. Once again, a number of questions came in that we're just not going to be able to answer live on the webinar. So what we will do is we'll answer all the questions. We'll type up all the answers to the questions, post them on our website with the recording, and then we'll provide an email to everyone who registered to the webinar to let you know that it's now available. So the last question we're going to take on is, what is the accuracy level of the SuperRegistration compared to ground control points? It's not really a direct comparison between the two because they have different functions. So ground control points are collected against a reference source and or survey points that have various levels of accuracy requirements depending on your actual project and depending on the deliverable that you're providing. So even control points between ortho images might have different accuracy requirements. In terms of SuperRegistration, because of its automation and because it's really a post-ortho process, so it's run on already ortho-rectified imagery in order to just make sure that all of your imagery has a really nice, tight alignment. It collects, so what it does is it actually collects a very dense network of highly accurate, statistically accurate control points or reference points between one of the images in the stack and between the images in the stacks, I guess. And with that dense network, we also have rigorous blunder detection algorithms that go through to identify potential errors or incorrectly matched reference points or control points that we then throw away. And we have a very high rigor in terms of what's collected. Oftentimes they have to have a pixel accuracy of less than 1/10 of a pixel, and that's how we're able to achieve the level of subpixel accuracy that Jason showcased today, where we've had a lot of projects where we've actually achieved or gone beyond the 1/10 pixel accuracy. But in what we showcased here today, we're approximately about 1.2 pixels, so about a 20th of a pixel accuracy. So with that, unfortunately, it's the last question we'll be able to get to, and a whole bunch more came in. So we, once again, really, really appreciate your time here with us today. We hope you found this webinar informative, and we would, if you have more questions that you want, feel free to reach out to us, and we would love to get on a call with you, have an email exchange, and ideally set up a demonstration where we can show you the details of how this workflow works. So once again, really appreciate your time on behalf of Catalyst. We hope you have a great day.